Chocolate snaps, caramel stretches, peanuts crunch, nougat pulls, 4 distinct textures, 15 peanuts per bar. One engineered system. 15 million bars leave this factory every single day. The structural question. But here's what most people don't understand. How do you mass produce something this layered without losing balance? Because at industrial scale, even one structural flaw doesn't just ruin one bar, it can collapse the entire production line. 1 degree too hot, the caramel floods the nougat. 1 psi too much, the chocolate cracks instead of snapping. Zero margin for error. 15 million times per day. Engineering tension. If caramel flows too quickly, it floods the nougat base and creates soggy, unstable bars. If nougat moisture shifts by even 2%, it sags under the weight of caramel and peanuts. If chocolate tempering fails, even by half a degree, the coating blooms, softens, and loses that signature snap. Millions of bars leave this facility every single day. The slightest deviation gets multiplied on a planetary scale. This isn't candy making. This is precision confectionery engineering. Signature moment. Inside the system. Today we step inside the billion candy bar factory, where the world's best-selling chocolate bar is manufactured with microscopic precision. Chocolate engineering. The process begins in West Africa, where raw cocoa beans are harvested from cacao pods. Beans are fermented for several days, then dried and shipped to processing facilities where they're roasted at controlled temperatures. Roasting develops chocolate flavor through Maillard reactions. Temperature and time determine everything. Too hot and beans taste burnt. Too cool and flavor never develops. Roasted beans are cracked and winnowed. Nibs are ground into cocoa liquor, a thick, dark paste that's the foundation of all chocolate. Sugar and milk powder are blended in precise ratios. Then the mixture enters conching, where rotating arms refine texture for up to 72 hours. Finally, tempering stabilizes cocoa butter crystals. Chocolate is melted to 113 degrees Fahrenheit, cooled to 81 degrees Fahrenheit, reheated to 88 degrees Fahrenheit. This precise thermal cycle creates stable crystal structure. Without proper tempering, chocolate would bloom, developing white streaks from unstable cocoa butter. It would soften at room temperature, it would lose its snap. Tempering is non-negotiable. The physics of chocolate demand it. Peanut roasting. Raw runner peanuts arrive in massive 1,000-pound totes from the American Southeast, primarily Georgia, Alabama, and Florida. These aren't just any peanuts. They're specifically selected for size, oil content, and crunch potential. The peanuts travel through a 150-foot convection oven at precisely 350 degrees Fahrenheit for exactly 30 minutes. Oscillating conveyors ensure even exposure to heat. Every peanut must roast uniformly. No dark spots, no pale sections. Roasting develops deep, nutty oils essential for both flavor and crunch. The Maillard reaction strikes again. Proteins and sugars react under heat to create hundreds of flavor compounds. Temperature sensors monitor internal peanut temperature in real time. If heat distribution shifts, the entire batch gets rejected. After roasting, the peanuts are immediately cooled to lock in flavor and prevent over-roasting from residual heat. Exactly 15 peanuts per Snickers bar. Not 14, not 16. 15. Caramel production. Corn syrup, sugar, butter, sweetened condensed milk, and salt combine in industrial-scale copper kettles. Under vacuum, the mixture cooks to precise viscosity at around 240 to 245 degrees Fahrenheit. This isn't approximate, it's exact. Why vacuum? Reduced atmospheric pressure lowers the boiling point of water, allowing caramel to cook faster without burning. Temperature and timing determine everything. Cook to 240 degrees Fahrenheit, and the caramel flows. Cook to 250 degrees Fahrenheit, and it becomes brittle candy. The window is 5 degrees. Too thin, and it floods the nougat. Too thick, and it becomes impossible to chew. Inline viscometers measure flow characteristics in real time. Paddle mixers ensure uniform heating, no hot spots that would cause scorching. The caramel must be slightly chewy so peanuts stick to it, but it can't be sticky or it gums up machinery. It can't be hard or it breaks teeth. This is caramel engineered to exact specifications. The Goldilocks zone of confectionery physics. Nougat formation. The nougat base is where structural engineering meets food science. Corn syrup and sugar are heated to create a thick syrup base. Then comes the critical step, whipped egg whites. Egg whites are proteins that, when whipped, trap air bubbles and stabilize them through protein networks. This creates the light, aerated texture. The egg white foam is carefully folded into the hot sugar syrup. Timing is critical. Add it too fast and the heat collapses the foam. Too slow and the syrup crystallizes. Peanut butter is blended into the nougat at this stage, creating the signature Snickers base that's different from Milky Way or Three Musketeers. Humidity is enemy number one. The facility maintains 40 to 45% relative humidity. Higher, and the nougat absorbs moisture, becoming soggy and unstable. Lower, and it dries out and cracks. The nougat is pressed between chilled stainless steel rollers, held at exactly 41 degrees Fahrenheit, which define the exact thickness of the base layer to within 0.5 millimeters. Cold rollers create a skin on the nougat surface. This skin prevents the nougat from sticking to equipment and provides structural integrity for the next layer. Layer bonding. Roasted peanuts are mixed with warm caramel in a rotating auger mixer at precisely 120 degrees Fahrenheit. Too hot, and the caramel becomes too fluid. Too cool, and it won't bond properly. The peanut caramel mixture is spread evenly across the cooled nougat layer using precision depositors. Weight sensors verify uniform distribution. Every square inch receives the same amount. A pressing roller bonds the layers into a uniform slab. Pressure is calibrated to bond without crushing the nougat base or forcing caramel into air pockets. The bonded slab enters cooling tunnels at 60 degrees Fahrenheit for exactly 12 minutes. This stabilizes structure before cutting. Rush this step and the layers separate. Overcool and the caramel becomes too brittle to cut cleanly. Cutting and enrobing. Rotating circular blades, spinning at 600 RPM, divide the slab into precise strips. Then guillotine cutters shape individual bars. Each cut must be clean. Rough edges create weak points where chocolate won't adhere properly. Each naked bar, arranged on a wire mesh conveyor moving at exactly 120 bars per minute, travels through the bottom enrober, a thin layer of chocolate applied to seal the base. Then comes the dramatic moment, the chocolate curtain. Tempered liquid chocolate flows in a continuous curtain. Each bar passes through, coating all sides with a thin, uniform layer. The flow must be controlled precisely. Too much creates chocolate tails at the bottom, too little leaves gaps in coverage. Finally, a decorative roller with raised ridges applies the signature Snickers swirl on top. This is enrobing, the art of coating confections in flowing chocolate with millimeter precision. 8:45 to 9:30. Cooling and stabilization. The coated bars enter a refrigerated cooling tunnel at 55 degrees Fahrenheit. Chocolate solidifies evenly over exactly 8 minutes, locking in texture and structure. Cool too fast, and thermal shock causes the chocolate to crack. Cool too slow, and the caramel layer softens. Air velocity is controlled to prevent chocolate bloom from condensation. Temperature gradients are monitored in real time. As bars exit the tunnel, they pass through a metal detector. Every single bar, any metal contamination from broken machinery, loose fasteners, or foreign objects, triggers automatic rejection. Then comes vision inspection. High-speed cameras scanning for misshapen bars, uneven chocolate coating, or label misalignment at 500 bars per minute. From cocoa beans roasted in West Africa to peanuts grown in Georgia, from caramel cooked to 245 degrees Fahrenheit to nougat pressed at 41 degrees Fahrenheit, 4 textures merge into one balanced structure. The same Snickers in New York tastes identical to one in Tokyo, in Sydney, in Sao Paulo. Precision confectionery engineering at global scale. Temperature control measured in degrees, layer thickness measured in millimeters, timing measured in seconds, and every bite begins with structure. Next episode, how Oreo achieves perfect cream-to-cookie ratios at 500 million cookies per day. Subscribe for more deep dives into the industrial engineering that powers the world's most iconic products. Thanks for watching.